Welcome back to HDL for Digital System Design. I'm Dr. Mike Brofchek. This is a continuation of Topic 3, Procedural Combinational Logic, If, Else, and Case, Video 2 of 4. So let's dive right in. Okay, so first off, you're going to have the choice between whether or not to use if-elses or case statements every time you write an encoder um, versus a mux. What are you going to choose? So CPUs use instruction decoders that use case statements. Interrupt controllers use if else because priority matters. Bus arbiters often use case Z that also includes some don't cares. Each of these synthesizes to physically different topologies. In this course, we'll see using case in the ALU on opcodes. We'll talk about case statements again when it comes to finite state machines. We'll use if-elses when we're looking at memory for address decoding. And we'll see again case statements on UARTs. So we'll see these patterns show up over and over again. Good to have them down now. So first off, you might think that, hey, every time I have an if-else, I could use a case statement and they'll be interchangeable. We kind of alluded that that might be the case in some instances when we were looking at building out muxes of different sizes. But is that always the case? Do you really just get to pick whichever reads nicer? Well, not exactly. So if-else statements are basically priority encoded. So what that basically means is that earlier conditions have shorter combinational paths, and the first match wins. Um, Although in some cases, depending on how it's structured, if statements, if it's just an if set, not if-elses, if it's pure ifs, it's the later one that matches. So if-elses, early ones match. If it's chained ifs statements, later ones win. Versus case statements that happen in parallel. All branches are compared at the same time. There's no priority. So different topologies, different timings, sometimes different LUT counts, depending on if we have wide cases. So if priority matters, so we can think of interrupts or masking errors. If, else if matters, right? That's definitely a pattern you'd want to use. So if priority matters, think if, else ifs. On the other hand, if you're looking at things that are mutually exclusive, right, where there can not be any possible overlap, then looking at things like op decoding, state decoding, use a case statement. The parallel topology is going to be faster. You don't have this chained approach. Everything can happen in parallel. So let's look at if, else if, basically chaining these priorities. So imagine again, you have this always block with a wildcard sensitivity list, as we expect, has a begin and an end. And what we see internally here is a chain where the very first thing in the chain has the highest priority. If A, then we set y equals to basically 1. Else, if B, then 2. Else, if C, we'll set it to 3. Else, otherwise, the absolute lowest priority prevents us having a latch, by the way, right? Because that else catches everything. We get 0. So this does synthesize into a structure of cascading muxes. The way that I generally think about this is every time you add in an else if, you're adding a mux to the chain. So a signal A reaches Y through mux 1, right? So basically it's either A or it's not. If it's A, you immediately get an answer. If you're going all the way to C, you've got to go through the first mux that checks if A was true. If it's not, then you're going to check if B is true. And if it's not, you're going to go, is C is true? That's basically 3 muxes to get to your answer of C. So you can see that cascading. So if you get a super wide chain, right? If you have if else's that have potentially, 8 or more priorities, you're getting a very deep timing bottleneck because each of those checks is going to cascade and take longer and longer. So in general, if I have priorities, I'm going to reach for an if else if priority chain. recognizing that if I have lots of different priority channels or choices, it's going to take longer and longer the deeper and deeper I go. So um, compare that to the parallel case, where perhaps what I want is I want all choices are equally likely and they don't overlap in any way. So here we go. We have four choices for potentially, in this case, an opcode, an operation that I want to do. It's never going to be the case that any of these could be, um, I will say they could occur at the same time. They are all mutually exclusive. I'm going to either have the bits on or off, never going to be some other situation here. So what we basically get is we can go and look at every branch simultaneously. Um, all four of the results are computed at the same time, and the opcode essentially picks the result it needs. Do recognize here that in this particular case, we have a default condition. You can imagine that that is important just in case, for whatever reason, one of those bits comes through as unknown or it takes, for whatever reason, um, that is something we need. So what's nice about this is that the delay is the same across no matter what branch we take, it is the exact same. There's no cascading of time. Everything gets computed in parallel. So um, there is also another interesting case statement called case Z for don't cares. And so here is, I'll say a question. Well, what happens if that your input, your request is 1011? What do we want to do? Where do we go? Which grant would win? Is it going to be the first one or the second one, right? Which one? Because in theory, we have don't cares here, and we have 1011. That will only match, I think, one place. And let's double check. So the answer is 3D4. Yep, this very first one here. Because essentially pattern matches, most significant bit is 1, and it matches that pattern, right? 1 is the most significant bit, it gets granted. You'll notice that this is constructed in such a way that there's never an opportunity for more than one of these to be true. So there you go. So you can use case Z, but you should probably never use case X. So case X treats X as a wildcard, much the same way that case Z does, but it can hide some simulation bugs where X basically um, should trigger a failure. So almost every modern linting tool would yell at you for trying to use case X. Okay, so your turn. Can you predict the hardware that is created here with these? Basically, I've got an 8-way decoder implemented two different ways. Which one do you think is faster? On the left, I have a case statement, which will do a case off of an input select, and it will be essentially 8 possible options on the output there. And on the right-hand side, I have a chain of 8 if else ifs um, that goes all the way through. I'll tell you right now that the functional output is equivalent, but what do you think the LUT count is, or maybe the critical path? Basically meaning uh, what's the longest timing path? Are they the same? Are they different? What does that look like? I'll give you a moment to think about it. All right, so welcome back. Hopefully you can see that case A would synthesize probably to something very balanced. This could be a balanced mux. If you look at eight things to decode, the shortest possible tree for that is about 3 levels deep, um, right? Because essentially you take the log of the size, you get a nice balanced binary tree. Um, version B, though, this if-else chain, is going to synthesize to a chain of essentially 7 deep. You're going to get your first if, right? Select 0. That is either true or false. If it's true, you're done. If it's false, you're now going to check, well, is select equal to 1? If it's true, then you're done, but you've gone through 2 checks there, 2 different muxes, right? If none of these are true, if select is 7, you will have gone through 6 other checks before you get to that last check, right? And so you can imagine that's pretty deep. So it is a lot slower, especially the wider you go. Um, there are times where Yosis might optimize B if it can figure it out, but you shouldn't rely on it. You should use the case statement when you want things to happen in parallel. All right, so let's take a look at a demo. Let's look at a 4-bit ALU, an arithmetic logic unit, using the case statement. So this will be in lecture examples week 1, day 3, sample 2 or segment 2, example 1. We'll make a simulation. It'll just look at every opcode. We'll do a waveform and we'll end with make stat. So first up in this directory, we'll do a make sim. And really quickly, you'll basically see here a handful of tests. We are going to try add, subtract, anding, and oring, and we'll make wave real quick and take a look at that. So let's see what that looks like. So there is essentially us doing the make sim. You can see a handful here of all of the different potential options. Let's actually take a look at this real quick. Let's look at um, that ALU real quick, just so you can see it. So you'll see here, essentially we have a handful of things being defined, but what we really care about is this case statement here, where we are computing a carry and a result based off of sum, carry and a result based off of subtraction, and we're also looking at potentially doing an and an or, and a default case here of all 0. So essentially that is our setup, and at the very end we do an assign here, essentially all 0 on the outside. For the 0, don't need to worry about it quite yet for what we're doing. What we really care about is internally here, this case statement. So let's take a look at the waveform that generates. So what we have here, let's add it in our ALU here. Let's look at our design under test here. Append these inputs. There we go, A and B, an opcode, carry, result 0. Actually, if we pull in the check, we'll get a few more things as well, just to be able to see them. So what I'm going to do here, we have in our test bench some nice naming things that we've done. So let's change that to ASCII. One of the things I also recommend is this opcode is really an enumerated data type. Now, sometimes GTK wave plays nicely and you can do a data format and an enum and define it. Other times it's not as nice. And what you can do though is you can create a filter that essentially translates different values into what you want. So this comes in real handy. I'm going to show you that here in a second, but let me enable transfer filter file, enable. I'll show it to you after I start it up. So I'm going to add this in on the opcode. So data format, translate, enable and select. We're going to do this one, hit OK. You'll notice that my 0, 0 became add. How does that work? It's actually super simple. Let's take a look at this filter file that I created earlier. Literally all I've done is I've taken the 4 opcodes that I know, 0, 0, 0, 1, 1, 0, and 1, 1, and mapped them to words that I can read. If you look, those match perfectly. 0, 0 is add, 0, 1 is subtract, 1, 0 is and, 1, 1 is or. And I've basically just done that here in this filter file and named it .gtkw for basically GTK wave. So that's the filter file. I right-clicked on the signal that I cared about, data format, translate filter file, and translated it by selecting that file. So all of this is to show you that we have created a case statement based solution to decoding our ALU opcodes. What you'll see here, we've got A and B are the inputs, right? They're all 4-bit values. Opcodes are 2 bits. We get a resultant out. And right now we don't need to worry about these expressions here. These are being used at the test bench level, but what you could look at is you could look at the words here at the bottom. So our first test was add 3 plus 5. So you can see 3 plus 5 here, add them together, and we get an 8. All right. Next, 15 plus 1, we expect to see a carry. 15 here, F, right? If you want to see that in numerical form, data format decimal, we'll do that for both of these. And the output here, the result, we can change that to a decimal also. So output is 0 with a carry of 1. 15 plus 1, that's exactly what we expect, right? 16 is all zeros on the first 4 bits and a carry of 1. Subtraction, 7 minus 3. 7, 3, subtract, result is 4. All right, and so on and so forth. So again, just quickly showing a case statement in order to derive these outputs based off of the opcodes provided. So, all right, let's move on real quick. We can also take a look at, we saw our outputs. We saw all these come through. We could also take a look real quick at the stats. So why don't we do that? Let's see what was actually built. So make stat real quick. And what we'll see here is we have 25 LUTs, 8 carries, handful of other things, but in general, that's the big cost to us, 25 LUTs and 8 carries. So let's continue on. So what are the tool build? I just showed it to you. Roughly, we've got 2 4-bit carry chains that are going to basically cause those 8 carries. We've got some op logic plus our 4-to-1 result mux that yields those 25 LUTs. So again, the 8 carries come from our 2 carry chains that we need, one for the add, one for the subtract, which tells us that we don't have independent add and subtracts. Well, we have independent add and subtracts. It's not reusing that logic. 25 LUTs, and that, by the way, that makes sense, right? We have those add and subtract occurring in parallel. So if they're parallel, we need hardware that does both of them. So you might ask yourself, is there a way that we could actually reduce that carry chain if we somehow maybe had a hybrid approach here? Potentially. Okay, 25 LUTs. They cover our per operation bitwise logic, as well as the 4-to-1 mux that picks between add, subtract, and an OR. So we need 33 total cells for a 4-bit 4-op ALU. This is going to scale pretty much linearly with the number of operand widths and operation counts that we have. So double check this, right? Why don't you take the ALU that we put in here and double it, see what happens, right? See if this does grow linearly. If you want to, add in a multiply. What is that going to take? That's going to take you adding in another opcode. It's not going to fit now in 4 bits, that's one thing. And see what it does in terms of the number of total LUTs needed and carries. All right, so you should check the machine as always. Ask it to explain the timing difference between an 8-way if-else-if chain and an 8-way case in Verilog after synthesis. So go ahead and ask it. Predict, right? I mean, if you were to think that the case statement should use O of log n, right? It's going to build a very nice compact tree, right? So basically the depth of searching is log of your total input space. And then if you do an if-else chain, right, the priority chain, it's going to be O of n, right? There should be roughly a chain that is, right, n long. If you have 8 things to select from, it will have 7 comparisons to make. So, you know, those are things to consider. All right, so I assume, or you should assume, that the AI is going to mention priority chain and a mux tree. But if it says that they're equivalent, that AI model is probably weak and not what you would want to use. So you could verify this, synthesize both, compare the depth reports, There are expressions you can pass in to figure out how many levels of logic this is using. All right, so big takeaways for what we just talked about. Use if else if you are talking about priority chains. If things happen in parallel, use the case statements. It'll create essentially parallelized muxes, form a tree form that gets progressively smaller. So use case when all of your alternatives, all the pathways are equal. But if priority matters, again, use if else. Use case Z if you have don't cares, but never use case X. All right. Finally, you should get into the habit of using default statements as well as a final else statement. Never leave a hanging choice, right? The final else basically is a catch-all, right, for your logic. Same thing, a default statement is a catch-all. Include those. If you don't include those, you risk introducing a latch, basically behavior that is now no longer purely combinational and it becomes sequential if you don't do this. So please include a default statement or an else, depending on which way you're going. Write out your intent. The synthesizer can only optimize what you told it you wanted. Okay? So just remember, it can only do what you told it you wanted. All right, so we've brought it up a handful of different ways. We are going to spend a lot more time on the latch problem. I keep saying, always include a final else or include that default. Video 3, the next video in this sequence, is going to explain that in more detail. Skipping either basically leads to an inferred latch. All right. So the inferred latch is not something you want. It is probably the most dangerous silent bug in combinational RTL, right? As soon as you introduce a latch, you introduce some really interesting timing issues, but it is, again, not syntactically wrong. So you have to figure out how to learn to spot these issues. I will give you a couple different ways to prevent it and hunt for it in code that you already have or that you're looking at. So until next time, go build some cool stuff.